Okay, so this will be Lecture 5, Part 3, and in this lecture we're going to explore complex numbers. It's going to be a little more advanced than what you may have encountered recently in algebra. We're going to introduce some new concepts, new things you can do with complex numbers. Quite a bit of it, though, however, will be a review. So let's get started. So Lecture 5, Part 3. Okay, all right. So with complex numbers, of course, the definition of a complex number is it's a plus bi is the format of a complex number. Or of course, I squared, as you may recollect, is equal to -1. And the typical variable we'll use for complex numbers is variable z. So z is equal to a plus bi. And we say that the real part of z is a and the imaginary part of z is b. And of course, we define complex multiplication, the product of two complex numbers. We essentially use FOIL. And then when you FOIL the two complex numbers together, it resolves into this term for the real part of the product and the imaginary part of the product. Right? And then, of course, we can add and subtract complex numbers, which resolves into a complex number with a real, and that I should not be there, that I should be there. Okay? All right. So, for instance, 3 plus 5i plus, okay, and so right here, what I expect you to be able to do is say multiply 3 plus 5i times 4 minus 2i, or add those two complex numbers or subtract those two complex numbers. And then, of course, there's the notion of raising a complex number to a power, and we know that I to the first is equal to I squared is equal to -1, I cubed is equal to -I, and I to the fourth, that's -I, and then I to the fourth is equal to 1. Okay, so I expect you to understand this from your algebra experience. Okay, I to the fourth is 20. So I to the 23rd, of course, then would be written as I to the 20 times I cubed. And of course, we know that I to the 20th is nothing more than I to the fourth raised to the fifth power. Okay, times I cubed. And of course, I to the fourth is 1, so 1 to the fifth is 1. So this is equal to I cubed, which is equal to -I. Okay, so I think you probably recall that from your algebra experience. If you're not accustomed to this or not comfortable with this, get with me, say during a break or after class or during my office hour, and we can do some more review types. For sure, there'll be quite a few web-assigned problems on this topic. All right, so let's get to some interesting stuff. So, for instance, for topic 3 of this lecture, we could talk about a further review items. So, pull up another page. So, we talk about complex conjugate. So if I give your complex number z is equal to a plus bi, then z bar is the complex conjugate of z, and effectively what you do is you flip the sign of the imaginary part. So the complex conjugate of a plus bi would be a minus bi. And it turns out that a complex number multiplied by its complex conjugate is equal to the square of the real part plus the square of the imaginary part. So for instance, all right, so let's take the complex conjugate of 3 plus pi I, and that turns out to be 3 minus pi I. Right, and in part 4, we see what we're doing is we're rationalizing a complex ratio, and by rationalizing that means we reformat this complex ratio so that the denominator contains only a real number and not a complex number. And to do that, you multiply upstairs and downstairs by the complex conjugate of the denominator. And so this is a multiplication, not a subtraction. It looks like a subtraction. That's a multiply. Okay, and so you'll FOIL the numerators and FOIL the denominators. But here in the denominator, you have a complex number multiplied by its complex conjugate, and then if you just use this formula, then the denominator will become c squared plus d squared, and all you have to do really is to FOIL the numerator, the two products in the numerator, the two factors in the numerator, and then the result is this. So this would be how you would rationalize a, I guess that would be the term, rationalize a complex fraction. All right. So algebra review concepts. Okay. So another thing we could talk about is the principal square root of a number. So this would be topic 5. Okay, so let's pull up another page. So in the principal square root of a number, so versus the regular square root. So the principal square root returns only a positive quantity. Okay, there's only one value. The principal square root of a function is a single valued output. Okay, and we contrast that with the regular square root, which is a multi-valued output function. All right, so in the principal square root, suppose that we want to take, say, the square root of negative r, where r is some, I don't know, perhaps some positive number. Although we'll leave it for now. We'll call it a positive number. So the square root of negative r, of course, is perceived to be like this. We can factor the two terms. So this essentially is -1 times the square root of r. And of course, the square root of -1 is defined to be I. So that would resolve to I times the square root of r. So that's where that comes from. Now, the regular square root is computed by simply taking the principal square root of the number and then affixing a plus or minus sign. So you have two outputs for the regular square root. So another issue is when we multiply two complex numbers, and so for instance, consider this problem. You don't multiply the two complex numbers, the square roots of two complex numbers, as you would do the product of the square roots of two real numbers. Okay, it is incorrect to say that the square root of -2 times the square root of -3 is equal to the square root of -2 times -3, which is equal to the square root of 6. That's wrong. You don't do that. When multiplying the square roots of two negative quantities, you first convert the square root quantity, the square root of the negative quantity, into its complex representation. So in this case, the square root of -2 becomes I times the square root of 2. And the square root of -3 becomes I times the square root of 3. And when you're multiplying those, then you now have the problem transformed so that you can go ahead and multiply the square roots of two real numbers. And you use the usual rules. Okay, and then the I times I, of course, resolves to -1. So this is the proper form right here. So be careful with that. There may be a couple of WebAssign questions requiring you to do so. And then, of course, you could have a situation like this, where you're multiplying two factors that are expressed in radical notation. And the two factors could be complex numbers. So in this case, you have a complex number right here, obviously. So the process of multiplying them, you would first convert each factor into its representation, where you have a real part and you have an imaginary part. Its representation, that is, in terms of A plus or minus. Okay, in this case it would be A minus IB times A, that should be a plus right there. Okay, that should be A plus I, or actually C plus, that would be C plus ID. So there's a typo there, a right O. So this should be C plus ID. Okay, and so you FOIL them, of course, and so the answer would be 36 plus, that should be a plus. 36 plus what? I times 12 times the square root of 4 minus I times 3 times the square root of 3 and then what, minus I squared times the square root of 12. And then you proceed to simplify that, so that would be 36, collect the real terms, so 36 is real, and then this would be plus the square root of 12, so that would be the real part of the product, and then you would add to it the complex part, so that would be 12 times the square root of 4 minus 3 times the square root of 3. So that would be how you would analyze this problem. Okay, and so I think you may have done this quite a bit in algebra. All right, so what else? Let's see, check the lecture notes. All right, so we can talk about the quadratic formula and its solution. So let's see here. Let me get So recall the quadratic formula, which is ax squared plus bx plus c is equal to 0. And then here's the solution to the quadratic formula. Now I have a, as I mentioned in the chapter 1 lecture notes, the subscripts 1 and 2 are placeholders for the two solutions to the quadratic formula. Okay, so remember that x sub 1 is equal to the negative of b minus the square root of b squared minus 4ac all over 2a. And then, of course, x sub 2 would equal to the negative of b plus the square root of b squared minus 4ac all over 2a. All right, so we have these results. So for instance, consider this example. We want to find the solutions to this quadratic formula, 4x squared minus 24x plus 37. So x1 comma 2 would equal to the negative of b, here's your b, here's your a, and here's your c. Okay, so the negative of b, which is 24, because here b is negative 24, so the negative of b is 24, plus or minus the square root of 24 squared, minus 4ac, all over 2a. Okay, and so using your calculator after simplifying, you discover that the two solutions, x1 comma 2, would equal to 24 plus or minus the square root of negative 16 over 8. And so, of course, as an aside, the square root of negative 16 resolves to I times 4. Okay, so that's I times 4. And then, of course, we divide I4 by 8, and so that's 1/2 I. So the two solutions would be 3 plus or minus I over 2. All right, so pretty straightforward stuff. Okay, so what do we have now? Oh, yeah, I have a note in the solution to that quadratic problem we just solved. Let's go back. Whenever a quadratic formula has two complex roots, something you should note that the two complex roots will be complex conjugates of each other. So in other words, if 3 plus I over 2 is a solution, then 3 minus I over 2, which is a complex conjugate, is another solution. All right. Okay, so let's see here. Next topic, right? Okay, so now we can talk about the polar form. So let's see, is this topic 4? Okay, yeah. Okay, so I guess we'll move on now to Lecture 5, Part 4. So this will be Lecture 5, Part 4. Let me check. Yeah, so we talk about the polar form representation of complex numbers. Okay, so let's deal with that. and graphing complex numbers as well. So something I don't know if we did too much in algebra, but we'll give it a go. So here, polar form. So in this case, I essentially have a complex plane. So we have a Cartesian plane, a polar plane, and now we have the complex plane. That's yet another coordinate system, and it kind of looks like the Cartesian coordinate system, and it can, in a sense, be viewed as such. But bear in mind that along the perpendicular axis are going to be complex, the imaginary parts of the complex number. So for instance, 1 plus I would be represented as this point in the complex plane, whereas 3 plus 2I would be represented as this point in the complex plane. So the real part is 3, and the imaginary part is 2. Negative 1 minus 2I would be represented here, and so forth. And we can graph complex numbers, ranges of complex numbers. So for instance, suppose we want to graph the set of complex numbers where A is less than 1 and B is greater than 0. So it would be this space right here shaded in purple. All right, so now we can represent complex numbers in polar form as well. So let's see. So if we kind of view the complex plane as a Cartesian plane, then for instance, A plus BI, again, A would be the real part, B being the complex part of the number. And if we let R, which in this case this is equal to the square root of A squared plus B squared, and that's called the modulus of a complex number. Okay, so we have what's called the modulus. So the radial arm length in the polar plane for a complex number is the modulus of the complex number. So for instance, if we have the complex number 8 minus 5I, then the modulus would be 64 plus 25, which is the square root of 89. Square root of 64 plus 25, which is the square root of 89, because you take the square root of the real part squared plus the imaginary part squared to get the modulus. So that's your radial arm, and then you can pretty much guess or anticipate what theta is going to be. Theta is going to be the inverse tangent of B over A. So, and of course, the sign of the inverse tangent of A will depend on which quadrant theta is written in. Okay, so so that would be theta. All right, so let's do some. I guess we'll have some practice problems representing complex numbers in polar form. Oh, well, here we can do another graph first before we proceed. Let's do some graphics work here. Okay, so suppose we want to graph the set of complex numbers where the modulus is less than 1. So we know, so to solve this problem, we know that the modulus of z kind of looks like the absolute value of z, but it's read modulus of z is equal to the square root of x squared plus y squared. Okay, because z is equal to x plus iy. All right, so if z is equal to x plus iy, then the modulus is equal to x squared plus y squared, and that's less than 1. So we can square both sides, okay, and in doing so, if we square both sides of the inequality, we'll have x squared plus y squared is less than 1. So the way you would sketch the graph is shown here. This would be the real axis. This would be the imaginary axis. So you would draw the unit circle with a dashed line, because the boundary of the unit circle is excluded by the inequality symbol. And then instead of putting 1 here, you would put I, and instead of putting -1 here, you would put -I. So this is the set of Z, and of course you would shade it in. So this would denote the locus of complex numbers where the modulus is less than 1. Okay, it turns out to be a circle shape in the complex plane. All right, so polar form of a complex number Z. Now, let's see, how can I explain this? Yeah, so we have, if Z is equal to A plus BI, we can effectively say that A, the real part of a complex number, is equal to R cosine theta. Or again, theta is the subtending angle formed by an initial side on the real axis and the terminal side determined by the placement of the complex point in the complex plane. Okay, so the complex point formed by the complex number in the complex plane forms a terminal point for the terminal side of an angle in the complex plane. So A, of course, is equal to R cosine theta, and which is basically your x value, and then B is equal to R sine theta, okay, which is basically your y value, the imaginary part of your complex number. And then R, of course, is equal to the modulus of your complex number shown here, and then the subtending angle is the ratio of the imaginary part over the real part. Okay. All right. So, for instance, if we wanted to represent 1 plus I. All right. So now this is new stuff for complex numbers. Okay. If we wanted to represent 1 plus I in polar form, as shown in this first illustration in Figure A, so we start off by saying, okay, the R value would equal to the square root of 1 plus 1, 1 squared plus 1 squared. Okay, which is the square root of 2. And then theta, of course, since we're in quadrant 1, would be the inverse tan of 1 over 1 in quadrant 1, which of course is 45 degrees or pi-4 radians. So the complex representation of this complex number would be R is the square root of 2 times the cosine of pi-4 plus I sine pi over 4. Okay, like so. All right, so that would be the polar representation. And one way I know it to memorize it is it's basically written as R cis theta. Okay, where cis is cosine, I is complex I, and S is sine theta. So you can use, I often lapse into the terminology R cis theta as a short way of writing it. Okay. All right, so let's go to part B. How about we extract out the polar representation of -1 plus the square root of 3i. So in this case, it is a quadrant 2 complex number, or the terminating, or the point resides in the quadrant 2 of the complex plane. So R is what? The square root of -1 squared plus the square root of 3 squared. Okay, and that's equal to the square root of 1 plus 3, which is 2. Okay, so our radial arm length is 2. Now we need to calculate theta. So theta would be inverse tan of what? The square root of 3 over -1. Okay, and so that would equal to what? Square root of 3 over 2, so that would be pi 6, right? Pi over 6. So that would be pi 6 radians. That would be the reference angle, pi 6 plus, now that would be the, okay, so the inverse tan of the square root of 3 is pi 6. So since we're in quadrant 2, that would be, so our reference angle is pi 6, so this would be 5 pi over 6. Okay, so 5 pi over 6, so the polar representation of -1 plus 3i would then be 2 times the cosine of 5 pi over 6 plus I sine 5 pi over 6. All right, see how that works? Okay. And then let's see, we have the other case, so let me erase this, make room. Part C of this problem, we want to represent the polar form for, what's that, -4 times the square root of 3 minus 4i, as shown in the illustration, shown in green. Okay, so this would be what? Let's see. Let me check the recording, make sure it's still working. Okay, so the recording is still working. Okay. So z is equal to -4 on the square root of 3 minus 4i. So the modulus of z then would equal to the square root of -4 on the square root of 3 quantity squared plus -4 squared, which is equal to the square root of, what, 16 times 3, that would be 48, plus 16, which is equal to the square root of 64, which is 8. So the modulus is 8, and then now we're in quadrant 3, so that means that the tangent, we would want to take the inverse tan of 4 over 4 on the square root of 3. Those both quantities are negative, right? And so this would equal to, I believe, pi thirds, right? Radians. That would be the reference angle. So the reference angle right here is pi thirds. So we just add pi to it. So that would be 4 pi over 3. So that would be the measure of angle theta in radians. All right, so then z, represented in polar form, would be 8 cis 4 pi over 3. Where cis is cosine 4 pi over 3 plus I sine 4 pi over 3. So you can write it this way if you're in a hurry. I don't know if you can do that on WebAssign, though. All right, and then D is done pretty much like Part A. Not much difference. You just have to figure out what theta is. That would be the only hard part. All right, so polar representation of complex numbers. That should be new stuff for you guys. Okay. Oh, wait. Did I get... Okay. I'm seeing here, I'm checking the notes. I think I got the angle wrong for Part C. Let's see, what did I say? 4 pi over 3? Let's see, square root of 3 over 1/2. Is this right? No, it's not right. That should be pi 6, right? Because the cosine of pi 6 is 1/2, and the sine of pi 6, oh, okay, so I did get that wrong. I'm sorry. Sorry, guys. That should be 7 pi over 6. I should go back and study the familiar angles again. Okay, my mistake. That's 7 pi over 6, so change that. And I think that'll affect the answer. I probably got it wrong in Part B as well. Okay, so let's go back and check Part B. Sorry, I got my familiar angles messed up. Let me check Part B again. Oh, I erased Part B. Let me rework Part B again. Sorry. Boo on me, right? Okay. Hello. Let's work Part B again. Yeah, that's the bad thing about doing video lectures. I don't have students challenging me on my mistakes. Okay, let's do Part B. So again, the theta for the complex number. So theta is equal to inverse tan. This is Part B. inverse tan of the square root of 3 over 1, negative 1. Okay, so the reference angle for this would be pi 6, right? Let's see, pi 6. Yeah, so that's equal to 5 pi over 6. I believe I said 5 pi over 6, did I not? Okay, so the reference angle is 5 pi over 6. Yeah, so I think I got part B right. If I said 5 pi over 6, then we're good. Okay, so just if I didn't, just make that adjustment in the solution for part B. Okay. No, it's not 5 pi over 6. It's 2 pi over 3. What is going on here? Did I get it? Check again. It's not 5 pi over 6. The inverse tan of the square root of 3 over negative 1. Okay, so sine of the square root of 3 over 2. No, wait, I'm sorry, what am I writing? That's square root of 3 is equal to square root of 3 over 2 divided by 1/2. And so we know that the sine is, oh, I'm sorry, the sine, that would be 1/2. That would be pi third. Yeah, okay, I'm sorry, that's pi third. So the reference angle, yeah, so there's the mistake I made in part B. The reference angle here is pi thirds. Sorry, it's a late night. Okay, so that means that this angle would have to be 2 pi over 3. So go back and correct your notes. For part B, make theta equal to 2 pi over 3. Just substitute theta equals 2 pi over 3 because I got the wrong reference angle. Okay, I mistakenly thought it was pi 6. It should be pi thirds for the reference angle for this particular theta. Okay, slight mistake. I think we got it straightened out now. All right. Okay, so what would be the polar representation of a product of two complex numbers? So we can figure out what that formula would be. All right, so let's do this. Okay, so next slide. Okay, so for instance, if Z1 is equal to R sub 1 times cosine theta 1 plus I sine theta 1, and Z2 is equal to R2 times cosine theta 2 plus I sine theta 2. Now, the product of the two complex numbers would be the product of the radial arm length, so that would be R1, R2, and then times cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. So again, what you'll do is you will FOIL these two factors, okay? So cosine theta 1 times cosine theta 2, okay, first. Then the outer would be cosine theta 1 times I sine theta 2. So where is that? Cosine theta 1 times I sine theta 2 is right there, but it's a complex number. And then the inner would be I sine theta 1 times cosine theta 2. Okay, so we sum those up. And then finally we multiplied the last term, so that would be minus, okay, the last term's right here, minus sine theta 1 sine theta 2. Okay, so now how do we simplify that? This can lend itself to some significant simplification. If you look at the real parts, and if you recall the definition of the cosine of the sum of two numbers from Lecture 4, then this, of course, is nothing more than the cosine of theta 1 plus theta 2. And then if you look at this particular sum for the imaginary part, that, of course, would be the sine of a sum of two angles. So interestingly enough, when you multiply two complex numbers and represent it in the polar plane, you take the angle at least would be, or the complex part would be the cosine of the sum of the angles plus I times the sine of the sum of the angles. And then you would finish it off by multiplying it by the magnitudes or the moduli of the two complex numbers. And we'll do an example here. Okay, and for division, instead of adding, the angles in the quotient. You just subtract the angles in the quotient. And of course, Z2 is not 0, and then you just divide the two moduli. Okay, and so I'll leave this to you as an exercise to validate that. Again, you'll probably have to do some rationalization, and then to calculate the quotient. All right. Okay. So, for instance, let's have Z1 times Z2. So Z1 given in polar form is here, and Z2 given in polar form is here. So the solution then is to multiply the moduli together. So this is not 25, but that's 2 times 5. Okay, it's 2 times 5. And then you add the angle. So pi fourths plus pi thirds, which is 7 pi over 12, plus I times sine of pi fourths plus pi 12, which is 7 pi over 12. And then I abbreviate the solution as 10 cis 7 pi over 12, or cis, of course, cis 7 pi over 12. Okay, is a shorthand notation for cosine 7 pi over 12 plus I sine 7 pi over 12. Okay, all right. So just take note of that. There's some efficiency there. Okay, so we can, of course, work on the division of the two complex numbers. All right, so we can let's work an example division. If we were to divide Z1 by Z2, the result would look like this. Okay, so Z1 over Z2, again, would be the moduli, the quotient of the moduli, and then you just subtract the two angles. So in this case, pi fourths minus pi thirds is negative pi twelfths. So it would be 2/5 C, negative pi twelfths. Okay, so there's your quotient. And why do we do this? So that brings up the next topic, which is de Moivre's theorem. So let's talk about de Moivre's theorem, which basically allows us to take powers of complex numbers without having to do any kind of unnecessary expansion. So with de Moivre's theorem, it goes like this. If we're given some complex number, Z, and we convert it to polar representation, okay, then we can deduce its power series like this. Okay, so if Z is equal to R times cosine theta plus I sine theta, then we have Z to the power of N, okay, where N I would take to be, in general, N would be an element of the positive integers. Okay, this is a capital Z. So this means N is a positive integer. So Z to the power of some positive integer, all you do is you raise the modulus to the nth power, and then you multiply theta by N. So Z to the N would be R to the N times cis N theta. So for instance, consider this example, 1/2 plus 1/2 I to the 10th power. All right. So what we can do is we first convert the complex number to its polar representation. So here's the modulus of the complex number, and then here's the polar part, cosine of pi fourths plus I sine of pi fourths, and we raise it to the 10th. And so all we do is we take the square root of 2 over 2, okay, raise it to the 10th power, which is this, and then we multiply it by cosine of 5 pi over 2, which is found by multiplying pi fourths by 10. Okay, and then we simplify. Okay, so we simplify. We know that the cosine of 5 pi over 2 is 0. Okay, and we know that the sine of 5 pi over 2 would be I over, let's see, that would be, where's 5 pi over 2? This is pi over 2, 3 pi over 2, 4 pi over 2, that would be 5 pi over 2. Okay, yeah, and so that would be essentially, this would be I, so that would be I, this is an equals, and so this would be, so what is 2 to the 5th over 2 to the 10th? 2 to the 5th over 2 to the 10th is 1 over 2 to the 5th, right? Which is 1/32. Okay, so the answer is I over 32. So Dumont's theorem, you may have had that. I don't think you had that. No, you did not have that in algebra because you didn't have cosine theta in algebra. All right, so how to raise complex numbers to powers. Okay, all right, now, in as much as we can raise complex numbers to powers, we can take the roots of complex numbers as well. So we can talk about the nth root of complex numbers. So let me give you the formula first, and then I'll do an example. Okay, so the formula for the nth root of a complex number is this. All right, so we have z in its polar form, which is equal to r times cosine theta plus I sine theta. And then we talk about z to the 1 over n power, where again, n is a positive integer. And so the letter w, subscript k, represents a root of the complex number. And so pay attention to the formula. The nth root of a complex number means that you'll have n roots. You're going to have n answers to this problem. All right, so the magnitude of the complex number essentially would be r to the power of 1 over n. And then the different numbers originate from using this formula. First of all, you calculate the subtending angle of the complex number, theta. And then you compute the argument to cosine theta and to sine theta by taking the subtending angle of z, okay? And then you add to it 2k pi, and then you divide by n, all right? So, and k, of course, varies from 0 to n minus 1. So you start off with k equals 0. Okay, so suppose, like, for instance, okay, before we go to the example, suppose, for instance, we wanted to take the 4th root of a complex number. All right, so let me show you how you fill in the numbers. So we want this, the 4th root. So that means that k would go from 0, 1, 2, and 3. You use these different values of k. So you're going to have 4 solutions to this problem. So you'll have W0, which would equal to r to the 1/4. That would be a real number, times cosine of whatever theta happens to be. Okay, and then 2, since k is 0, 2 times 0 is 0, so this would be theta over n, but n is 4. So that would be theta over 4 plus I sine theta over 4. Okay, so that would be one of 4 answers. Right, and then W1 would be found by plugging in k equals 1 into the formula. So W1 would be r to the 4th times cosine, and then the angle would be theta plus 2 pi over 4, all of that over 4. Okay, plus I sine theta plus 2 pi over 4, like so. Okay, and then W2, okay, would be found by plugging in 2 for k, so that would be r to the 1/4 power times cosine of theta plus 4 pi over 4 plus I sine theta plus 4 pi over 4. Okay, and then finally we have to process W3, right? So W3 would equal to r to the 1/4 times cosine of theta plus 6 pi over 4 plus I sine theta plus 6 pi over 4, all of that. Okay, so so now we can do a numeric example. So you see how the expansion goes. So z to the 1/4 will have 4 numbers, and of course you can plot these 4 numbers in the complex plane. All right, so let's see here. Let's go to another page and do an example. How about we calculate the 6 roots of -64 and plot them in the complex plane. So I'll show you how that works. Let me pull up the drawing. So here we want the 6 roots of -64, -64 to the 1/6. So the first thing you want to do is you want to convert the -64 to its polar representation as a complex number. So we know that -64 would equal to 64 times the cosine of pi minus the I sine of pi. Now you know I sine of pi, of course, is 0, cosine of pi is -1, so -1 times 64 is -64. And since we're taking the 6th root, we're going to have k goes from 0 to 5, so as shown here. Okay, so we're going to find the 6 roots right there. So k is 0, k is 1, k is 2, k is 3, k is 4, k is 5. All right, so that would be the first thing you would set up. And then, of course, the second thing you would set up is you start off by taking the 6th root of 64, which, of course, is 2. So here's the real part. The radial arm length is 2 right here. All right, and then in general, you have the cosine would be pi plus 2k pi over n, which is 6, plus I sine 2 pi plus 2k pi over 6. All right, so then you start off with 0, plug in 0 for k here. Okay, so you see this k right there, plug in 0. And so that would be cosine pi 6 plus I sine pi 6. Okay, and then when you simplify that, cosine of pi 6, of course, is the square root of 3 over 2, and the sine of pi 6 is 1/2. So the square root of 3 over 2 plus I sine 1/2 times 2 becomes the square root of 3 plus I. So that's 1 root, 1 of 6 roots. Okay. Now we use k equals 1, and so pi plus 2 pi is 3 pi. 3 pi over 6 is pi halves, and then so we would have 64 to the 1/6 times cis of pi halves. So we know the cosine of pi halves, of course, that's 0, and the sine of pi halves is 1, so we would have 2i as the root. Okay. Now we go to the 3rd root, where k is equal to 2, so that would be 5 pi over 6, 64 to the 1/6 times cis 5 pi over 6. Now, the cosine of 5 pi over 6, of course, is -1/2, and the sine of 5 pi over 6 is the square root of 3 over 2. Let's see, is that right? The sine of, yes. No, let's see. There we go again. The cosine of 5 pi over 6 is the square root of 3 over 2. I beg your pardon. I should really have a table at hand because I'm always mixing those up. The cosine of 5 pi over 6 is the square root of 3 over 2. Okay, and the sine of the negative of square root of 3 over 2. Okay, from my familiar angles table. And then the sine of 5 pi over 6 is 1/2. Okay. Okay, so now then we just simplify it. We get the negative square root of 3 plus I. All right, and then I'll let you trace the remaining 3 by plugging in k equals 3 into the formula k equals 4. And then here are the graphs. Here are the plots of the 6 roots of -64. Okay, labeled W0, W1, W2, W3, W4. Notice that they're all symmetrically apart. So in other words, if the square root of 3 plus I is a root, then its conjugate is a root. And if negative square root of 3 plus I is a root, then its conjugate is a root. And if 2I is a root, then its conjugate is a root as well. So if you can calculate the first 3, then just take the conjugates of those 3 to get the next 3. Okay. All right. So that is if n is an even number. If n is an odd number, say if you were to take the 7 roots, then of course you would probably have 1 real number, and the other 6 would be complex conjugates. Yeah, of course, the 7th root of a negative number is, of course, a real number. Yeah, okay, so that makes sense. All right, so the nth roots of complex numbers. All right, so let's, in this example, the next example, I'll calculate the cubic roots of 2 plus 2i. and I'll just walk you through that one. Okay, so we have okay, so let's calculate the cubic roots of 2 plus 2i. So we resolve z into its polar representation. Then we use our general formula wk would equal to the cubic root of 2 on the square root of 2, okay, which is 2 to the 3/2 to the 1/3 power, which is the square root of 2. All right, so you have to be a little bit proficient with your exponents and laws of exponents here to be able to pick out the square root of 2 as the real part, or the multiplier part for the polar form. And then it would just be, oh, and so now we're using angular measure here. So just replace 2 pi with 360 degrees, and so it would be 45 degrees plus 360 degrees k over n, which is 3, all right? And so first we use k equals 0, so it would be square root of 2 is just 15 degrees. Then we use k equals 1, which would be what, 405 degrees, so 405 degrees, what is an angle coterminal? We know that 135 degrees is coterminal with 405 degrees. And then k equals 2, so that would be 720 plus 45 degrees, so 765 degrees, so minus 720, let's see, 360. So what angle is coterminal with, is that right, 720, 765 degrees. So this would be 360, 720, okay, and then, why is it 225? Where did that come from? 45 degrees plus, oh, we have to divide by 3, I see, I'm sorry. Okay, I see. I forgot to divide by 3. So 45 plus 720, I'm on k equals 2 now, plus 720 divided by 3. So what is that? That would be 765 over 3, which is equal to 225. Okay, so that works out. So that's where the 225 comes from. All right, just an algebraic mistake. And then you plot the 3 roots in the complex plane, and you can see they're equidistant apart on the circle of radius square root of 2. Okay, and the square root of 2 right here comes from right there. That's square root of 2. They form like a little BMW symbol, a propeller. Okay, what else in section Lecture 5.4? Is there anything else? Okay, so that would be it for Lecture 5.4. Please do your web assignment for these. This particular section has high importance. Right, and so the next topic, of course, we'll talk a lot about some physics and engineering type problems. A lot of word problems on the foreground. So until then, we'll see you.